Welcome to this deep dive. We're taking a fascinating leap today, straight into the heart of particle physics.
Mm.
Think about it. We're sort of on the verge of a new era in how we understand the universe's most fundamental building blocks.
Yeah, and it's all thanks to some, seriously cutting-edge quantum technology.
Exactly.
For decades, our main tool for exploring, everything matter, energy, space, time, has been the particle accelerator.
Right, smashing things together.
Pretty much. We collide particles at incredible speeds, and they create these spectacular showers of new particles. Then scientists have to painstakingly analyze these subatomic fireworks.
Trying to unlock the deepest secrets of the cosmos from the debris, essentially.
Precisely. But the complexity is just... it's mind-boggling. Imagine trying to understand how a car engine works by, blowing up thousands of them at once and then sifting through the wreckage.
Okay, yeah, that paints a picture. That's kind of the scale we're talking about.
It really is.
And now we're gearing up to build even more powerful accelerators, right? Pushing the limits even further.
We are, and that means the challenge of making sense of those particle avalanches just gets exponentially harder.
Which brings us to this idea of a paradigm shift. I think Maria Spyropoulos from Caltech called it that.
That's the term she used, yeah. We fundamentally need new tools in our scientific toolbox. We have to be able to process what these next-gen collisions will actually show us.
So enter the quantum sensor.
Exactly. That's the tool generating a lot of buzz right now. These are incredibly sensitive devices designed to detect individual particles with the precision we've really only dreamed of until now.
And it's big collaboration driving this.
Oh, absolutely. It's bringing together brilliant minds from places like Fermilab, Caltech, JPL, many other top institutions too.
Okay, so let's unpack that a bit. Quantum sensors.
Mm-hmm.
What actually makes them so incredibly sensitive? What's the secret sauce?
Well, their extreme sensitivity comes from how they use the strained rules of quantum mechanics. This lets them interact with individual particles in ways that, traditional detectors just can't.
Okay.
And the specific type we're diving into today is the superconducting microwire single photon detector, SMSPD for short.
SMSPD.
Got it. And recently, a team put these SMSPDs through their very first real-world test at Fermilab.
Fermilab, known for its incredibly high-energy beams. It sounds almost counterintuitive, doesn't it? Putting these super delicate quantum devices in the path of particle beams.
It does sound a bit like that, almost like sending, a fine teacup into a hailstorm, but somehow expecting it to tell you the size and speed of every single hailstone.
Huh. Okay, so what happened? Did the teacup survive?
It did more than survive. The results, they were published in the Journal of Instrumentation, were actually truly remarkable.
Really?
Yeah, they exposed the SMSPDs to high-energy beams, protons, electrons, pions, the kind of fundamental particles that pop out of these collisions.
Okay.
And they showed the sensors weren't just highly efficient at detecting them, but they did it with significantly better time and spatial resolution compared to our current detectors.
Wow, both. That really does sound like a game changer. I think Shi at Fermilab said something like, this is just the beginning.
He did, yeah. And he even hinted at the possibility of detecting much lighter, more elusive particles, maybe even, the stuff that makes up dark matter.
Which would be huge.
And
absolutely massive.
It really would. And what's quite interesting is that the basic technology behind these SMSPDs, it isn't entirely brand new.
Oh.
No, they're closely related to something called superconducting nanowire single photon detectors, SMSPDs. And those have already been making waves in other really advanced fields.
What?
Things like quantum networks, even astronomy. So you see this real sort of cross-pollination happening between different scientific areas.
Okay. So it's kind of like taking tech designed for, say, peering deep into space, detecting single photons from distant stars, and adapting it to look at the absolute smallest building blocks of matter right here. That's pretty cool.
It is. For instance, the team at JPL, who are real leaders in this SMSPD tech, they've used them in their deep space optical communications experiment.
Sending data over vast distances using lasers, right?
Incredible amounts of data, yeah. And the same core group with researchers from Caltech and Fermilab, too, they've been using these sensors in the IonQNet program.
What's that?
That's research right on the frontier of quantum teleportation, which is, a fundamental step towards building a future quantum internet.
Wow. Okay. So if the SMSPDs are already doing all that amazing stuff, why the need for SMSPDs specifically for particle physics? What's the key difference?
It really boils down to size, for particle physics at least. The SMSPDs, they can be made with a much larger surface area compared to the nanowire versions, the SNSPD.
Okay, larger area. Why does that matter so much in a particle collision?
Well, think about it. After a collision, you get this chaotic spray of countless particles flying out in all directions. A bigger detector surface just gives you a much better chance of catching more of those particles.
Right, gives you a more complete picture of what actually happened in the event, like using a bigger net to catch more fish.
Exactly. You need a bigger net for a really crowded environment.
Makes sense.
And, as Hichi pointed out, the really new thing in this recent study, the breakthrough, was proving that these SMSPDs can efficiently detect charged particles.
Ah, not just photons.
Right. Detecting charged particles wasn't really a critical requirement for the quantum networking or astronomy uses, which mostly focus on photons, uncharged particles of light.
So being able to detect the charged stuff opens up a whole new application for them in particle physics.
Precisely. A whole new realm of possibilities.
Okay, so they're bigger, they can detect charged particles.
Oh,
That sounds like a significant improvement already. But then there's this term 4D sensing that keeps coming up. Sounds very sci-fi. What does that actually mean here?
yeah. 4D sensing sounds impressive, doesn't it? What it really means is the ability of these SMSPDs to simultaneously get both better spatial resolution, knowing where a particle hit, and better time resolution, knowing exactly when it hit.
Ah, okay, because usually there's a trade-off.
Often, yes. With traditional detectors, you might have one that's great at pinpointing the location or another that's great at timing the arrival. But getting both at super high precision at the same time has been a real challenge.
So it's like, imagine trying to track one specific person walking through Grand Central Station during rush hour.
Mm-hmm.
You need to know exactly where they are in that huge crowd at any given moment. That's the spatial part.
Right.
But you also need to know the precise time they pass a certain point, the temporal part, to really follow their path, especially when there are like millions of events or people moving around every second, just like in a collider.
That's a fantastic analogy. It captures it perfectly. And Maria Spiropoulos really emphasized this point. As particle collisions get more and more intense, producing just unbelievable numbers of particles,
The timing becomes crucial.
absolutely vital. You need that precise time tagging to sort out the truly interesting fundamental interactions from just, the background clutter.
So in older experiments, maybe just knowing the where was enough.
In many cases, yes, or the timing wasn't needed with such extreme precision. But now the when is just as important as the where. The key thing is, this 4D capability lets us disentangle these incredibly complex collisions much more effectively than we could before.
This really does sound incredibly promising for the future. So what's next? Are we likely to see these SMSPDs actually being built into the next generation of huge particle colliders being planned?
That is definitely the hope, yes. That's the direction the research is heading. There's a huge amount of excitement about the potential role these could play in future big projects.
Like the Future Circular Collider, the FCC.
Exactly, like the proposed FCC, which would be even more powerful than the LHC, or potentially a muon collider as well.
And the lead scientist on this at Fermilab is Christian Peña.
That's right. Christian Peña, along with a really talented international team, is spearheading this push.
And just so everyone knows, this specific groundbreaking work we've been talking about, that was published in the Journal of Instrumentation, wasn't it?
It was, yeah. March 4th, 2025. The paper's called High Energy Particle Detection with Large Area Superconducting Microwire Array.
Right. And it was a big collaborative effort funded by the U.S. Department of Energy, Fermilab itself, ANID in Chile, and the Federico Santa Maria Technical University.
Absolutely correct. It really shows how global and collaborative this kind of cutting-edge science is nowadays. And you had key researchers involved from Caltech and JPL2, people like Christina Wang, Adi Bornheim, Boris Kors, Jamie Luskin, making really significant contributions.
So zooming out then, the big picture seems to be that we're really standing on the threshold of a new chapter in how we actually see and understand the fundamental bits of our universe.
I think that's fair to say. It's all thanks to the incredible sensitivity and, crucially, the combined space and time precision offered by these quantum sensors like the SMSPDs.
Giving us a level of detail we just haven't had before.
Exactly. And that's absolutely critical if we want to make sense of the, frankly, overwhelming complexity inside these future high-energy particle colliders.
And it's not just about getting sharper pictures of the particles we already know exist.
No, that's the really exciting part. It genuinely opens up the possibility of discovering entirely new fundamental particles. Maybe, just maybe, finally shedding some light on what dark matter is actually made of.
finding those components that make up so much of the universe but are currently invisible to us.
Precisely. By giving us this much more detailed, more nuanced view of what happens in these collisions, we significantly boost our chances of spotting those really faint, subtle signals. The kinds of signals that might have been completely buried in the noise with the older detectors.
It could potentially revolutionize our whole understanding of the cosmos, right down at the most basic level.
It really could. It's kind of amazing, isn't it, to think that something operating at these incredibly tiny quantum scales could hold the key to understanding the sheer vastness of the universe.
It absolutely is. It really makes you think, doesn't it? How breakthroughs in what might seem like niche scientific areas, quantum sensing in this case, can suddenly ripple out and have these profound impacts on the biggest questions we ask about everything. It really gets you wondering, what other unexpected connections, what other cross-disciplinary innovations might be just around the corner, ready to completely reshape how we see reality?
A fascinating thought to end on.
Thanks for taking this deep dive with us today.